Let's take a look at this problem. We have a merry-go-round rotating at 5 radians per second. A person 1 meter from the center of the circle moving linearly at 2.5 meters per second. And it says the person jumped off. So this must be their final velocity when they jumped off. So what is going to happen to the merry-go-round? Will it speed up or slow down? Well, let's zoom in and look at forces. So what are the forces present? Well, the first force that's present is I have something pushing the person. If they jump to the left, there must be a force on the person. So let's call this merry-go-round on man. I also know Newton's third law. I also have equal and opposite of that, force of man on the merry-go-round. Okay. Now we know that the merry-go-round doesn't move linearly, so it must have another force that is equal to that one. And we'll call this the force of the pole on the merry-go-round. Okay. So now, if we were looking at the forces, what will the merry-go-round do? Will it speed up or slow down? Well, linear motion, the acceleration in the x, well, it's pinned there. So acceleration in the x is 0. So that means that my net force has to equal 0. So I know force of man on merry-go-round must equal force of the pole on the merry-go-round as well. So that would lead us to believe it stays the same linear speed, which is correct. But what I need to look at is what happens to the angular speed. Well, let's look at these two forces and see which ones do a torque. Well, I look right here, I only have 2 of them. Okay. And this force, oops, it erased. Okay. Right here, the one I just drew in, that force goes through the axis of rotation, so that has no torque. Okay. My other force here, this one, has a torque. Okay, and which direction is that torque? Well, that is a clockwise torque. The object is already moving clockwise, so it is going to speed up. Okay. So I could say the object speeds up. I could say that the omega initial is clockwise. A clockwise torque causes a clockwise alpha, so that would be a good explanation there if I wanted to just make sure to cover all those aspects of angular kinematics. Next, if the person was 1 meter from the center and they jump off at 2.5 meters per second as shown, what is the omega final of the merry-go-round? Well, we've done this before, okay, and we've seen the net force in this scenario. Okay, I have 3 equal forces, okay, all in the same plane. So these forces cannot equal 0, so my net force does not equal 0. So change in momentum is not 0. That means momentum is not conserved. Okay, what about the torque net? Is the torque net equal to 0? I think it is, and let's check. Well, our first force, right, here I have this one that's highlighted in yellow. That does 0 torque. And then the other 2, right, which I'll highlight in green, right, these 2 both do equal and opposite torque, so my torque net equals 0. So if that's the case, torque net equals 0, then my change in angular momentum is 0, so angular momentum is conserved, so then I can do Li equals Lf. Now, looking out at this a little bit more, okay, let's solve it over here. So I have Li equals Lf. What has angular momentum to begin with? Well, I would look at it and say everything has angular momentum. I have a L total. They're all together. Afterwards, the person jumps off, so the person or the man has angular momentum, plus there is an angular momentum of the merry-go-round all by itself. Okay? Now, how do I calculate angular momentum of something rotating? Well, that is I total times omega total. equals, okay, in this scenario, to do the man, I would do, we said momentum times r perpendicular, plus, lastly, I of the merry-go-round times omega of the merry-go-round. So, I total, I would have to calculate this. So, to calculate this, I could plug in I of the man, which is going to be mr squared, because he's a point particle, plus I of the merry-go-round, which we're going to call 1/2 mr squared. These are different m's, so I'll do this massive man. Right? Times omega total, and omega total, the whole thing at the beginning is rotating at 5 rads per second. Remember, rotation is the same at any location. Now the man, I don't know his momentum, but I do know momentum is mv times r, perpendicular. Okay. Lastly, angular momentum of the merry-go-round, that is 1/2 mr squared times omega, which is what we're looking for. Right? I believe I have information for all of these things, and I am looking for omega final. Right? So, I know both masses. Right? I know the r's that are involved here. Okay? So I know all of that. I know my omega total. I know the mass. I know the velocity. I know r. So I know everything but omega. Okay? So now let's plug in our values. Okay? I believe in the previous problem our mass was 50 kilograms for the man. His r, we got to notice he's not at the whole radius, he's just at 1 meter. So this would be 1 meter squared plus half of the merry-go-round, which was 250, times its r, that's at the whole radius, 1.5 meters squared. Okay. All of that times the omega, which is 5 rads per second. Okay. And that equals the other side now. Okay. The man's mass is 50 kilograms times his velocity. Now, this is the big one you got to watch out for because it's velocity, so I have to pay attention to direction. The man is moving to the left, so his velocity is going to be negative 2.5 meters per second. Okay. Times r, again, he's acting at 1 meter. And lastly, plus half the mass, which we said was 250 kilograms, times the r, 1.5 meters squared, times omega final. Let me take a quick pause. So here, with my work, you can see, when I plugged in all this information, I got my 331 times my 5, then equals my negative 125, and then solved for omega. Again, you always need to check, do answers make sense? Well, right here, we said, what does the merry-go-round do? The merry-go-round speeds up. Okay? So it started off at 5 rads per second, and now I'm saying it is now going 6.33 rads per second. The next question, what would happen if they jumped the other direction? Okay, well, if they jumped the other direction, again, we could just look at our forces here. Okay? So if I wanted to simplify this down, okay, and look at my forces, okay, if they were to jump, okay, the other direction, then there would have to be a force on the man going this direction, and here we would have the force on the merry-go-round. Okay. So if I have a counterclockwise torque with clockwise velocity, I would slow